Welcome back to part two of my talk. Let me resume. We finished the first part with this geometric characterization. Let me recall it. And this was the result for, say, the critical case when the constant kappa was chosen equal to the Chigger constant h. So you take a planar domain. You take R to be the unique positive solution of the volume of omega t equal to pi times t squared if omega is non-x of radius r and if omega is a Jordan domain such that its boundary is a non-space filling curve, then this unique solution R is the inverse of the Chigger constant and your maximal minimizer is given by the union of all the bows of radius r. And we had something about also uniqueness, that is when the inner parallel set of distance r coincides with the closure of its interior, then E is as well minimal, and therefore it is actually the unique minimizer. So let me give you let us pass immediately to the case general kappa. The remarkable geometric characterization I gave you is a common feature for actually any kappa greater than or equal to the inverse of capital R. Okay, so we're going obviously we're going to lose something, that is, we're not anymore solving that equation because that was something very specific to the Chigger, to the, say, critical case. Now the theorem reads as follows. You take a planar domain, you fix any kappa, any constant kappa greater than or equal to the curvature of the greatest ball contained in the box inside omega. And well, if omega is a Jordan domain whose boundary is a non-space filling curve and omega is non-x of radius, the inverse of the kappa you fixed, well then the maximal minimizer of the functional perimeter E minus kappa times volume of E in the right class that we described in the first lecture is given by the union of all the bows of curvature kappa, okay, so that is of radius the inverse of kappa. And we have the same thing about minimality. So the exact same theorem that held for the critical case actually holds for any choice of kappa, right? You just need to replace h, the Chigger constant, with a general kappa. Okay? So very nice geometric characterization of maximal minimizers. Now, I would like to discuss a bit minimality, that is, minimal minimizers. So we have this say condition that ensures that this set we find here is also minimal, that is, the inner parallel set of distance r coincides with the closure of its interior. So it's so let me show you how it can fail this uniqueness. Okay, so I will give you this example that we call the Pinocchio shape. So we take a ball of radius, say 1. You take a ray exiting from the center of the ball, and along this ball you let slide a ball of some radius. Okay, you need to exactly tweak this radius. There is a chord size, such that you end with this shape. And for this shape here, the Chigger constant is exactly the inverse of the radius of this ball you're sliding outwards, okay? And so it's very easy to see that, okay, from the theorem we know that the maximal minimizer is the whole set. And now if you take this last ball and you start dragging it backwards, you can compute the change in energy. And it's very easy to see that in doing so you do not change the energy. So dragging this ball backwards, you continue creating minimizers, okay? And one can prove that the minimal minimizer is basically the ball of radius 1 union, this last in some sense ball here, okay? And well, why is uniqueness failing? Well, it is failing because you do not have this set equality, and you do not have this set equality because in the inner parallel set at distance r you have a one-dimensional submanifold, okay? That is this curve here, okay? So this is how uniqueness can fail, basically. It is basically the only way how uniqueness can fail. So a natural first guess, educated guess, that is the guess we ourselves made, is that the minimal minimizer is, well, the closure of the interior of the guy, Minkowski sum, the ball of radius r, okay? That is, we take the union of all the balls of radius r that are centered on the closure of the interior of the inner parallel set at distance r. But let us consider this set here, that is two balls, say of radius 1, linked by a very thin tube, and let us fix kappa to be the inverse of half the width of the tube, okay? So if, say, our guess is right, what we drawn in dark gray is the inner parallel set of distance r. What is it in light gray is this guy here, that is, say, our candidate minimal minimizer. So let's argue by contradiction, and let us suppose this guy here is a minimizer, okay? And we will basically do the same argument. Now, I will do a computation, but it's basically the same argument I did before for the Pinocchio shape. So if I wasn't clear before, I hope it will be clear now how it works. You basically take this last ball here, and you push it a bit forward inside the set, okay? Inside the tube. In doing so, you change the set. You basically add this yellow rectangle, so you change the energy. But how does the energy change? Your basic, the perimeter term changes by twice the length of how much you push the ball inside the tube, okay? What about the volume term? Well, the volume term changes as the volume of this rectangle, so you have the length, how much you push the ball forward, so L, times the width of the tube. So it's 2 times R times L. But the volume term, recall, is multiplied by kappa, and kappa is the inverse of this radius here. So kappa and R cancel out, and so you end up with the change in perimeter is 2L minus kappa times the change in volume is 2L. So in the end, the global change in the energy is 0. And this means that this guy here, if we started from a minimizer, this guy here is again a minimizer. So I keep pushing forward, and this again needs to be a minimizer. And I push forward and forward and forward, but at some point I arrive at this configuration. And from my hypothesis, from my reductio ad absurdum argument, this needs to be a minimizer. But this would be a minimizer whose interior boundary is not analytic, which is impossible. So our first natural educated guess must be discarded, okay? So what we did was to go back to the blackboard, and we studied the structure of the set difference inner parallel set at distance r minus the closure of its interior, okay? So we set omega to be a Jordan domain with non-exo size r, and what we proved is that basically only two different things can happen. So you have two families of smooth C11 curves with a bound on the curvature, such that, well, the curves, so the first family, are basically the curves we saw in the Pinocchio example, okay? So are curves whose with a, say, free endpoint, and the other endpoint is locked in the closure of the interior. And the curves in the second family are the curves we saw in the last examples. And there are curves whose both endpoints are locked to be on the closure of the interior. And this is basically all you can see in this difference, in this set difference. You have these two types of curves that make up all the set difference. And this is very nice, because at this point we can easily prove who the minimal minimizer is. And again, same set of assumptions on omega, a planar domain, actually a Jordan domain, whose boundary is not a space-filling curve, fixed kappa, positive, greater than or equal the curvature of the greatest ball inside omega. If omega is non-x or radius the inverse of this kappa, well then the minimal minimizer is the Minkowski sum of a ball of radius r with the closure of the interior of the inner parallel set omega union the image of the curves of the second type. So the curves we saw in that dumbbell example, okay? And when you put the theorem on maximal minimizers and this one together, and you know the structure of the set difference between of omega r with the closure of its interior, well, you find that actually you have uniqueness when you do not have curves of the first type, okay? And so we have a geometric characterization of maximal minimizer, one for minimal minimizers. And when the two things do not coincide, we do know why they don't. And they don't because you have some curves of type 1, say, okay? And well, this actually allows us to interpolate. You can interpolate from a minimal minimizer up to a maximal one in a continuous way in the volume. And the idea is just, you just draw this next. You start filling in a continuous way this next. You start moving a ball, okay, along these curves of type 1. And while you move this ball in a continuous manner, you build minimizers. You build a family of minimizer that is whose, say, volume is a continuous function, okay? So you can interpolate. And actually, we can prove that any minimizer of the energy is one of all these possible interpolations. So we really have a characterization for all minimizers of this energy at fixed kappa. And this is what I call the rigidity. And then we have some nestedness properties, that is, okay, suppose omega satisfies the assumptions of the theorem for two different radii, okay? Well, then we have the set inclusions, the maximal minimizer corresponding to the greater curvature contains obviously the minimal minimizer corresponding to the same curvature. This one contains the maximal minimizer corresponding to the smaller curvature between the two, which in turn contains the minimal minimizer corresponding to this second curvature. Okay, so we have these, say, nestedness, these boxing properties. We can box one into the other, the minimizer, whenever we can apply the theorem for different values of kappa. And well, this basically brings us to the isoperimetric problem. What we're going to do is we want to apply this theorem basically for all values of kappa. So we consider the following class. The class A of Jordan domains whose boundary is a non-space filling curve such that they have non-x radius rho for any choice rho. Okay, in between, say, 0 up to capital R, where capital R, again, is the size of the maximal ball containing omega. Well, then, if you pick In this case, you can prove that you do not have curves of type 2, okay? You can only have Pinocchio's, say, behaviors, okay? So the first example we saw. The second example will never happen in this case. So we can, if we put ourselves in this situation, we can prove that for any volume greater than or equal to the volume of the maximal ball containing omega, there exists a curvature, depending on the volume, greater than or equal to the curvature of the maximal ball, and a minimizer of the auxiliary function with this fixed kappa, such that this minimizer has the given volume, and well, this minimizer is an isoperimetric set. And then you can actually choose the family of minimizer to be increasing with respect to the set inclusion. So we're able to find all isoperimetric sets for this class of domains omega by solving the auxiliary problem. Okay? Because for small volumes, they're balls, and at some point, when you reach the size of the maximal ball, well, you start solving the auxiliary problem. And you find all isoperimetric sets. So we really know the shape of all isoperimetric sets. And this extends at a 1997 theorem that held only for convex sets. Okay? And what I would like to remark here is that this class is very wide and can contain wild sets. For instance, the Koch snowflake, whose boundary is a fractal, whose boundary has infinite perimeter, it has even not integer Hausdorff dimension, it belongs to this class. So if you give us the Koch snowflake, we know who all its isoperimetric sets are, which is kind of nice. And this more or less closes the part about the shape. We have now a good understanding of the shape of isoperimetric sets for a rather wide class of domains. And what can we say about the profile? Well, almost as a corollary, as a side effect of our result, it follows that the isoperimetric profile is convex. Okay, so I haven't been really precise in this statement. So the real statement is the following. You take a set in our class, and you consider the following map, G, that to each curvature associates minus the infimum of the energy of the auxiliary energy, so perimeter of E minus kappa times volume of E, among all subsets in the right class of competitors. You can prove that this map is convex. Its Legendre transform is defined on the range of volumes from the volume of the maximal ball inside omega up to the volume of omega, and this Legendre transform actually coincides with the isoperimetric profile. And this immediately tells us that the isoperimetric profile over this interval is convex, and this is because the Legendre transform sends convex map into convex maps. Okay? Then the isoperimetric profile, as I told you, is convex on this range, and actually on the first range from 0 up to the volume of the maximal ball is concave because it goes like the square root of the volume. So when you take the square of the isoperimetric profile, clearly it is linear on the first piece, it is convex on the second piece, and you can actually check that the gluing preserves in the gluing point convexity is preserved when you take the square, so that the square of the profile is globally convex. And well, actually we can also say that the derivative of the profile is given by the curvature of the minimizer, okay? But this is somewhat standard, this was somewhat already known, but this, if you want, is a confirmation of the fact. Okay, then as the very last thing, I would like to settle a question that I get very often, that is the following. There is a very important result by Couvert that states that the square of the profile is concave, at least when your box is convex, okay? And well, I'm saying that the square is convex, so I'm basically saying something that is in contrast with what Couvert said. And this is not my intention to call him wrong, and he is not wrong, but neither am I. The point is that there are actually two different profiles. You can consider the relative one, where you actually minimize the relative perimeter of E inside omega. That is, in this case, the perimeter of E inside omega whenever your set E has some boundary in common with omega that counts 0 in the energy. So you can stick to the boundary of the box for free. You do not pay anything on your energy, okay? And this is what Couvert studies. What we study is the total profile, where you look at the total perimeter. So if your competitor has some piece of the boundary shared with the box omega, it's going to pay, okay? Nothing is for free now, okay? And this different choice gives rise to different behaviors. As I told you, in the relative one, this is the result by Couvert, you get that the square of the profile is concave. In our case, the square is convex. Then there is, and if you want, this is some sort of analytical difference. Then we have a geometrical difference. In the first case, if you take a minimizer, it is known that its boundary touches the boundary of the box in an orthogonal fashion. In our case, if you take a minimizer, the minimizer touches the boundary of the box in a tangential way, okay? So this is just to make a comparison between the two different profiles. There's the relative one, the square is concave, and you have orthogonality of the boundaries. In our case, you have that the square is convex, and you have tangentiality of the boundaries. And this is more or less what I wanted to tell you, and this is pretty much all contained in a series of joint papers that have been written in collaboration with Gianpaolo Leonardi, who is based in Trento, and with Robin Neumeier, who is based in the US Northwestern University. So these are basically the papers where you can fetch the results. Some have been already published, and one other is currently submitted. I hope you enjoyed the talk and the results, and if you have any questions, feel free to drop me an email, or I believe there is going to be an open question session. Thanks again for attending.